So all properties come back to the arrangement and the strength of attractions between particles. Chemical properties are related to the bonds themselves. Most physical properties are related to the IMFs, or the interparticle attractions. So when we look at an ionic bond, we don't always use the word IMF because we don't have molecules. But in that, every single particle or ion is held to every other particle by an actual ionic bond. The same is true for network covalent and for metallic, which is why when we are comparing many of those properties, they are so different than the molecular solids, which are only held together by IMFs. With the first property here, conductivity of electricity, it's important to remember what allows for that, and it is the movement of charge. It could be the movement of electrons or the movement of ions, either cations or anions, which would allow our electrons and or our charge to be carried. Ionic compounds have charges, but they're stuck in place. They can't move. The electron has already been transferred from cation to anion, and it will stay there because of the strong attraction from the nuclei to those electrons. If we melt it, so that means take solid ionic compound like salt and get it up to 800, 900, 1000 degrees Celsius until it turns into a liquid, it would conduct electricity. In a liquid state, the particles are free to move. It has to be so hot to keep those attractions from reforming. The particles have to be moving that fast. We are much more used to dissolving. Not everything that dissolves can conduct. Covalent things can dissolve in water, but they don't conduct because they stay as molecules. Weak acids and bases, we'll see, can dissolve, but they don't conduct well because they form very few ions. Ionic compounds ionize either totally or significantly enough that those ions are freely moving around when they are dissolved in water. And it's not the water itself, but the ions in the water that are conducting. They are serving as electrolytes. In the next one, I slightly reworded the question to fit on the page here, but showing in terms of a picture. Particle diagrams are vital for going from just memorizing phrases about IMFs to understanding how the IMFs can be applied and explained. In a network covalent solid, this would be an example of maybe diamond. Every atom is bonded to every other atom by a covalent bond. They are held in place strongly. They are held in place at a certain bond angle, and they have to stay in that location. There is a little bit of vibration possible, but otherwise very little change in location or translation, movement of particles. When we have a molecular or covalent solid, it is held by IMFs. This is ice. We do have waters here that are held together by covalent bonds, but as my ice goes to water, I don't break down my H2O. I am breaking these dashed IMF hydrogen bonds. Those IMFs, even the strongest of them, hydrogen bonds, are hundreds, if not more times, weaker than each bond. And if these bonds are strong bonds in multiple directions, we get to an even stronger structure similar to ionic and even with metallic. So those IMFs, not nearly as strong, so the molecules can break free and move freely much more easily. Vapor pressure is an important property that's kind of the opposite of melting and boiling. A high vapor pressure means a lot of our substance has turned into vapor, or very much of it has evaporated, going from either the solid or liquid to the gaseous state. The things with the highest vapor pressure are the things that stick together the worst. Covalent molecular solids. They break apart into gases because they are held together by weaker IMFs, not by metallic, ionic, or covalent bonds in a network. Nonpolar covalent molecular solids tend to have the highest vapor pressure because of the weakest attractions, only dispersion forces.